Waukegan, Illinois, 26 May, 1943. A United States Navy Ordnance Inspector named Vesta Stout sealed a 2-page letter and addressed it to the White House. Inside, she described a recurring failure. Waterlogged paper pull tabs on ammunition boxes tore during live reloads under combat conditions. Within weeks, the War Production Board and Johnson & Johnson's Penicillin division began supplying a cloth-backed, waterproof, rubber-adhesive tape to ordnance depots. Soldiers would call it duct tape, later duct tape. That same year, American chemical plants accelerated synthetic rubber production to replace lost Asian latex. Penicillin moved from laboratory batches to industrial fermentation tanks. Standardized 20-liter jerrycans cut fuel loss and handling time. Instant coffee entered combat rations. Commanders expected temporary measures. The documented results tell a different story. Designs that outlived the emergency and became permanent fixtures of civilian life. Washington, D.C., 2nd January, 1942. A War Production Board circular landed on plant managers' desks across the industrial Northeast. The single-page document listed rubber, tin, and shipping tonnage under a new designation. Critical. Pre-war planners had assumed global commerce would backfill any shortages through neutral ports and stockpiles. Japanese forces changed that assumption in weeks, not years. By early 1942, the empire controlled more than 90% of Allied natural rubber sources in Southeast Asia. German submarines pressured Atlantic convoys, reducing available shipping tonnage by double-digit percentages monthly. Donald Nelson, chairman of the War Production Board, convened an emergency committee with Vannevar Bush of the Office of Scientific Research and Development and representatives from the British Ministry of Supply. Their directive was clear: replace what was lost or accept defeat through immobilization. The solution required coordination across chemistry, procurement, and tooling that had never been attempted at continental scale. The Rubber Reserve Program launched within weeks. Engineers at DuPont, Standard Oil, and chemical plants across Ohio and Texas worked to perfect emulsion polymerization of butadiene and styrene, creating GRS, a general-purpose synthetic rubber. Early Buna N trials had shown promise, but required refinement for tire treads, gaskets, and hoses. Simultaneously, the military redesigned combat rations. The new K ration, C ration, and 10-in-1 packs reduced shipping cube by standardizing dimensions and eliminating excess packaging. Consumer nylon production halted overnight. The polymer shifted to parachute canopies, suspension cords, and webbing. Baseline measurements documented the crisis. In 1941, the United States had imported more than 600,000 tons of natural rubber annually. By mid-1942, imports had collapsed to a fraction of that figure. Wound infection mortality rates stood above 20% in many theaters. Allied fuel cans leaked at rates exceeding 15% during transport and handling. Pre-war 2-gallon and 4-gallon tins corroded quickly and lacked secure closures. A War Production Board bulletin from January 1942 formalized the shift. Rubber is hereby designated a top priority strategic material. Civilian tire sales are curtailed, effective immediately. The directive acknowledged that national survival now depended on industrial substitution, not battlefield improvisation. Factories, not frontline ingenuity, would determine whether vehicles moved, whether wounded survived, whether operations succeeded. The mobilization fused laboratory research, procurement offices, and machine tool shops into a single system. Capacity, not creativity alone, would decide availability. Engineers understood that solving one problem created demand for 10 related solutions. Synthetic rubber required standardized molds. Standardized molds required unified specifications. Specifications required testing protocols. Protocols required inter-service coordination. By 1945, United States synthetic rubber output would exceed 800,000 tons annually, surpassing total pre-war Allied imports of natural latex. This represented an industrial substitution at continental scale, executed in under 4 years. The transformation was not metaphorical. It was measurable, documented, and permanent. Cambridge, Massachusetts, 12th of July, 1942. An Office of Scientific Research and Development Committee convened around a table stacked with draft protocols. Engineers had compiled adhesion tests, salt spray corrosion standards, and drop tests for ration packaging. The question before them was not whether standards mattered, but whether standardization could be imposed fast enough to matter. Theater commanders expected local workarounds and field modifications. The OSRD saw an opportunity to convert those fixes into interoperable products. James Bryant Conant, president of Harvard University and chairman of the National Defense Research Committee, chaired the session. British representatives, including advisors to Lord Beaverbrook's Ministry of Supply, contributed specifications from Royal Air Force and Royal Navy procurement. The United States National Bureau of Standards provided engineers familiar with industrial acceptance testing. Their goal was alignment, common threads, gasket materials, cap sizes, and test methods that would allow parts made in Michigan to mate with assemblies from Manchester. The protocols covered fuel cans, adhesive tapes, carton seams, and moisture barriers. Military threads received unified pitch standards. Gasket compounds faced salt spray chambers for 72 hours before approval. Can linings required phenolic coatings resistant to petroleum distillates. Ration cartons needed quick-open seams that functioned after 6 months in tropical humidity. Adhesives underwent peel and shear testing under immersion. Every specification included quantitative pass-fail criteria. One innovation arrived from an unexpected quarter. Royal Air Force pilots flying at high altitude reported that fountain pens leaked or froze, rendering navigation logs illegible. The RAF Procurement Office tested a Hungarian invention, a ballpoint pen using viscous ink and a rotating ball bearing. The design eliminated leaks and functioned at altitude. Within months, British and American suppliers began production. The military adopted the ballpoint pen as standard issue for aircrew. The most consequential technology under review was the cavity magnetron, invented by John Randall and Harry Boot at the University of Birmingham. The device generated high-power microwaves in a compact, reliable package, enabling airborne radar sets small enough for night fighters and maritime patrol aircraft. The OSRD contract brought the magnetron from laboratory prototype to mass production, with specifications for quality control, thermal management, and field maintenance. An OSRD procurement annex from July 1942 formalized the approach. Procurement shall mandate common acceptance tests and interchangeability where practicable. The phrase "where practicable" provided flexibility, but the directive's intent was clear. Components from different contractors would meet identical performance benchmarks. The cause and effect relationship was straightforward. Common gauges and test methods elevated first-pass manufacturing yields. Parts made by firms that had never collaborated could now be swapped in the field without performance loss. Maintenance crews no longer needed separate toolkits for British and American equipment. Depot inventories consolidated around fewer part numbers. Within 12 months, contractors across 2 continents produced components that locked together and passed the same acceptance tests. This was not merely efficiency. It was the groundwork for post-war civilian standardization, where consumer products would inherit military test protocols and dimensional tolerances. London and Cairo, 3 March 1943. Technical intelligence sketches of a captured Wehrmacht fuel can lay beside photographs of leaking Allied tins on a Ministry of Supply desk. The contrast was stark and measurable. British 2-gallon tins and American 4-gallon cans corroded within weeks, leaked during handling, and required 2 soldiers to carry safely when full. The German Einheits canister, which Allied troops quickly nicknamed the jerrycan, solved every problem simultaneously. The design was elegant in its simplicity. Pressed steel construction with embossed X-shaped stiffeners provided structural strength without excessive weight. 3 handles allowed 1 soldier to carry a full can alone, or 2 soldiers to share the load with better balance. The camlock cap used a captive rubber gasket that sealed reliably and could be opened without tools. Interior phenolic and enamel linings resisted both corrosion and petroleum degradation. British Ministry of Supply inspectors measured the performance difference. Allied tins lost fuel at rates between 15% and 20% during transport, handling, and storage. Corrosion, loose caps, and seam failures accounted for most losses. The jerrycan reduced wastage to negligible levels, often below 1%. Handling time measurements showed that a soldier could pour fuel from a jerrycan into a vehicle tank in less than half the time required for a traditional tin, and with less spillage. Quartermaster officers in North Africa documented the operational impact. A Middle East supply report from 1943 noted, "Loss on issue reduced to negligible, handling time halved." The same report calculated that fuel savings from jerrycan adoption in a single month equaled the cargo capacity of a small coastal tanker. That was fuel available for mobile operations without requiring an additional supply convoy. The Allied response was rapid and pragmatic: copy the design and manufacture it at scale. British and American plants began producing jerrycans in 1943. Engineering teams reverse-engineered the pressed steel tooling, the gasket compounds, and the interior coatings. Standardized spouts and pouring attachments followed. ensuring that jerrycans from different suppliers remained interoperable. The cause and effect chain extended beyond immediate fuel savings. Improved fuel delivery sustained the operational tempo of mechanized units. Depot planning simplified when wastage rates became predictable and minimal. Vehicles spent less time immobilized waiting for fuel resupply. The design proved so effective that it influenced post-war civilian fuel and water containers, with ISO standards eventually codifying dimensions and features derived directly from the wartime jerrycan. Field trials in multiple theaters confirmed the conclusion. The three-handle pattern, the cam lock closure, and the internal lining represented a categorical improvement over previous designs. The geometry was not a temporary expedient. It was a solution that required no further iteration. Modern fuel cans for civilian, industrial, and military use retain the same basic form. The wartime design solved the containerization problem once, and no superior alternative has emerged in 8 decades. Akron, Ohio, 10th April, 1943. A production board in a chemical plant displayed monthly GRS output against military tire requisitions. The numbers were climbing faster than early forecasts had predicted. Engineers from B.F. Goodrich, Firestone, and U.S. Rubber monitored polymerization reactors, adjusted catalyst ratios, and refined compounding formulas. William O'Neill, director of the Rubber Reserve Program, reviewed the data with British procurement liaisons. The question, was no longer whether synthetic rubber could work, but whether production could scale fast enough to eliminate rationing. Emulsion polymerization of butadiene and styrene required precise control. The process mixed monomers in water with soap emulsifiers, initiators, and temperature regulation. Catalyst selection influenced polymer chain length and cross-linking density. Engineers measured Mooney viscosity to ensure consistency between batches. Compounding for tire treads required different formulations than sidewalls, and both differed from gaskets, hoses, and seals. Pre-war planners had estimated that achieving viability would take years. Instead, multiple plants reached steady-state production within months of startup. By mid-1943, monthly output measured in tens of thousands of tons. A rubber reserve memorandum from that period set a national target greater than 600,000 tons per annum by war's end. The impact on fleet readiness was immediate and measurable. Tire rationing, which had threatened to immobilize civilian transport and limit military vehicle availability, began to ease. Predictable wear profiles simplified convoy planning. Maintenance officers could calculate tire replacement schedules based on mileage and load rather than scarcity and improvisation. Vehicle immobilizations from tire failures dropped as supply stabilized. Synthetic rubber also enabled new applications. Pipeline hoses for fuel transfer, pump seals for fluid systems, and gaskets for aircraft engines all required elastomers with specific properties. GRS variants filled those roles. The material was not identical to natural rubber in every characteristic, but it was sufficient for most military applications and superior in some. By 1945, United States synthetic rubber production exceeded 800,000 tons annually. That figure surpassed total pre-war Allied imports of natural latex. The substitution was structural, not temporary. American industry had replaced the rubber plantations of Southeast Asia with chemical reactors in the Midwest. The transformation extended beyond military logistics. Post-war civilian markets inherited the production capacity. Tire manufacturers, automotive suppliers, and industrial equipment makers shifted permanently to synthetic elastomers for many applications. Natural rubber retained advantages in certain specialized uses, but the majority of rubber products would henceforth come from polymerization plants rather than tree plantations. By VJ Day, the United States had effectively decoupled its rubber supply from tropical agriculture. The industrial substitution was complete, permanent, and measurable. A hemisphere once supplying latex had been replaced by factories that would continue operating for decades, producing millions of tons annually. Peoria, Illinois, 30th August, 1943. A fermentation room at the Northern Regional Research Laboratory recorded batch volumes in a logbook. Engineers monitored oxygenation rates, antifoam additives, and corn steep liquor concentrations. Howard Florey and Ernst Chain had demonstrated penicillin's therapeutic potential in controlled trials. Now the challenge was scaling production from laboratory petri dishes to industrial deep tank fermentation. The breakthrough came from agronomic research. Scientists discovered that corn steep liquor, a byproduct of corn processing, provided an ideal growth medium for Penicillium mold strains. Combined with forced aeration and temperature control, deep tank fermentation increased yields by orders of magnitude compared to surface culture methods. Strain selection further improved output. Researchers tested thousands of mold samples, eventually identifying strains that produced significantly higher concentrations of penicillin per batch. Stability remained a concern. Penicillin degraded rapidly in solution and under heat. Freeze-drying solved the problem. The process removed water under vacuum at low temperature, leaving a stable powder that could be stored for months and reconstituted with sterile water before use. Standardized glass vials with measured dosages, simplified field distribution and administration. The United States Committee on Medical Research coordinated clinical trials in military hospitals. Results were unambiguous. Wound infection mortality rates, which had stood above 20% in many theaters, dropped by double-digit percentages where penicillin protocols were implemented. Surgeons reported shorter hospital stays and faster returns to duty. The antibiotic was particularly effective against streptococcal and staphylococcal infections, which had been major causes of battlefield mortality in previous wars. A Committee on Medical Research report from 1944 documented the production scale-up. Monthly output now measured in billions of units, freeze-dried stability acceptable for field issue. By 1945, cumulative production reached trillions of units annually. What had been a scarce experimental drug in 1941 was now available in sufficient quantity for broad deployment across all theaters. The logistical infrastructure supporting penicillin distribution foreshadowed post-war medical supply chains. Sterile packaging, cold chain management, and single-use disposable items became standard practice. Powdered plasma used similar packaging and reconstitution protocols. Disposable tubing and sterile barriers reduced cross-contamination risks compared to reusable equipment that required field sterilization. Surgical throughput increased as infection rates fell. Hospital beds turned over faster. Fewer soldiers required prolonged care or medical evacuation. The strategic impact extended beyond individual lives saved. Reduced hospitalization times translated to higher force availability and lower logistical strain on medical transport and supplies. Post-war, the wartime, production methods became the foundation for the global antibiotics industry. Pharmaceutical companies retained the fermentation technology, quality control protocols, and distribution networks developed during the war. Penicillin production continued to expand, and related antibiotics followed similar development paths. By VJ Day, penicillin had transitioned from laboratory curiosity to mass-produced strategic material. The production infrastructure built in 3 years would define medical manufacturing for generations. The fermentation logs from Peoria documented not just batch yields, but the beginning of modern pharmaceutical production. Birmingham, UK, Toledo, Ohio, 5th October, 1943. Pressed steel halves of a jerrycan met at a weld line in a British Ministry of Supply facility. Across the Atlantic, a Willys Overland assembly line fitted chassis for the MB model, which Ford also produced as the GPW under license. The two products, container and vehicle, shared a common characteristic. They were designed for function, standardization, and interoperability rather than individual optimization. The jerrycan specifications had been finalized: 20 liters capacity, 3 handles arranged for single-soldier or 2-soldier carry, embossed X-pattern stiffeners for structural integrity without excessive weight, cam-lock lid with captive gasket, interior phenolic lining resistant to fuel degradation. Allied production ramped quickly once tooling was established. Standardized spouts unified pouring methods across British and American supplies. Depot handling metrics confirmed the operational advantage. Fuel transfer from jerrycan to vehicle tank took less than half the time required with traditional tins. Spillage dropped to near negligible levels. Loss during transport and storage fell below 1% in most cases. A European Theatre of Operations Logistics report documented the change. Fuel issue losses approaching zero post-conversion. Motor pool readiness rates improved correspondingly. The Willys MB and Ford GPW represented a parallel standardization effort. Total production reached approximately 640,000 units by war's end. Every vehicle shared the same parts catalog, toolkit, and maintenance procedures. Tread patterns standardized, towing points, stretcher brackets, and communications equipment mounting followed identical specifications. A spare part from a Michigan factory fit a Jeep assembled in Ohio without modification. The vehicle's roles extended beyond transport. Jeeps served as reconnaissance platforms, communications hubs, stretcher carriers, and light cargo haulers. The standardization meant that any soldier trained on one MB could operate any other MB. Maintenance crews required only one set of tools and procedures. Supply officers stocked fewer unique part numbers. The cause and effect relationship between containerization, vehicle standardization, and operational tempo was measurable. Predictable refueling enabled tighter march schedules. Standardized maintenance reduced downtime. Interchangeable parts simplified field repairs. Units maintained higher readiness rates because logistics became more predictable. Post-war civilian markets inherited both designs with minimal modification. The jerrycan geometry influenced fuel and water container standards worldwide. International Organization for Standardization specifications for portable fuel containers retained the three-handle configuration, cam lock closure, and capacity derived from the wartime jerrycan. Modern NATO fuel cans remain visually and functionally similar to 1943 production units. The Jeep platform evolved into civilian sport utility vehicles and light trucks. The concept of a standardized, multi-role, easily maintained utility vehicle became foundational to automotive design. Willys marketed civilian versions immediately after the war. Other manufacturers adopted similar configurations. The military continued using Jeep-derived designs for decades. A fuel container and a parts catalog did as much for mobility as engine horsepower. Both remain visible in contemporary automotive and fuel handling standards. The wartime emphasis on standardization, interoperability, and maintainability created design principles that outlasted the emergency that produced them. New Brunswick, New Jersey, Bridgeport, Connecticut. 12th January 1944. A tensile testing machine peeled a water-soaked tape strip from a wooden crate seam. Engineers at Penicillin, a division of Johnson & Johnson, recorded peel strength, shear resistance, and adhesion retention after 24-hour immersion. Across the facility, a ration assembly line filled moisture barrier envelopes with soluble coffee powder. Both products addressed failures identified by field personnel. Vesta Stout, an ordnance inspector at a munitions plant near Chicago, had written to the White House in May 1943 describing a specific problem. Paper tape used to seal ammunition boxes tore when wet, preventing soldiers from opening crates quickly during live reloads. Her letter was precise and documented. Paper pull tabs failed under field conditions, particularly in rain or mud. The boxes would not open as designed. The Quartermaster Corps tested alternatives. Cotton duck fabric backing provided strength and flexibility that paper lacked. Rubber-based adhesive offered water resistance. Permacell engineers developed a coated cloth tape that maintained adhesion under immersion and could be torn by hand without tools. The military adopted the tape rapidly. Field applications extended beyond crate sealing to cable bundling, temporary repairs, and dozens of improvised uses. Test reports documented the performance difference. Paper tape lost adhesion and tore easily when wet. Cotton duct tape maintained peel strength and remained removable without leaving excessive residue. Opening time for a standard ammunition crate dropped from approximately 1 minute to less than 30 seconds. That differential multiplied across platoons and companies translated to minutes saved during critical operations. Simultaneously, the Quartermaster Food Division addressed beverage preparation. Combat rations had included ground coffee, but brewing required percolators, time, and fuel. Nestlé chemists had developed instant coffee using spray drying and freeze-drying processes. The resulting powder dissolved in hot water in less than 60 seconds. Moisture barrier envelopes protected the product from humidity during storage and transport. Soluble coffee entered K rations and C rations in 1943. Troop acceptance was high. Field trial reports noted improved morale and alertness during extended operations. The product delivered caffeine and calories without requiring cooking equipment. Shipping weight and cube were lower than ground coffee, and brewing supplies combined. Another ration innovation addressed warm weather chocolate distribution. Standard chocolate bars melted in tropical heat. Forrest Mars and Bruce Murray developed a hard sugar shell coating that protected chocolate centers from heat and handling. The resulting product, branded M&Ms, starting in 1941, allowed chocolate to be included in rations deployed to hot climates. A Quartermaster test report from 1944 summarized the findings. Improved opening times and high troop acceptance for solubles, cloth-backed tape superior to paper under field conditions. The report quantified time savings and recommended continued procurement. Post-war, the products transitioned directly to civilian markets. Duct tape became a hardware store staple used for repairs, sealing, and dozens of household applications. Instant coffee brands scaled from wartime production plants with minimal retooling. M&Ms entered retail distribution. Consumers purchased wartime specifications under peacetime labels, often without knowing the product's military origins. The cause and effect chain was clear: seconds saved per box, predictable beverage preparation, and melt-resistant confections all reduced operational overhead. Standardized stimulants simplified supply planning. The products worked well enough that they required no significant redesign for civilian use. Malvern, UK, 20th February 1944, Waltham, Massachusetts, 8th May 1945. An engineer inspected a cavity magnetron beside an airborne radar set at the Telecommunications Research Establishment. The device, invented by John Randall and Harry Boot at the University of Birmingham, used resonant copper cavities to generate high-power microwave radiation. The technology enabled compact radar units small enough for night fighters and maritime patrol aircraft. Earlier radar systems had required large ground installations. The cavity magnetron made airborne interception radar practical. The magnetron's performance characteristics were measurable and significant. High Q-factor resonant cavities provided stable frequency output. Conduction cooling eliminated the need for bulky liquid cooling systems. Integration into aircraft nose cones and wing pods followed standardized mounting interfaces. Royal Air Force trial notes documented the operational advantage: output stable, range performance increased materially under adverse weather conditions. The device performed well in rain and sea clutter, conditions that had limited earlier radar designs. Night fighters equipped with magnetron-based radar intercepted German bombers with increasing effectiveness. Maritime patrol aircraft detected submarines on the surface at ranges that allowed attack before the submarine could dive. The tactical margins improved detection, tracking, and engagement across multiple roles. Post-war researchers at Raytheon Corporation in Massachusetts investigated commercial applications for magnetron technology. Percy Spencer, an engineer working with active magnetron units, noticed that a chocolate bar in his pocket had melted during testing. The observation led to systematic experiments with food heating using microwave radiation. The physics was straightforward. Water molecules in food absorbed microwave energy and converted it to heat through dielectric heating. Raytheon filed patents for microwave cooking devices in the late 1940s. Early commercial units were large and expensive, targeted at industrial and restaurant applications. Engineers developed safety interlocks, waveguide designs, and shielding requirements to prevent microwave leakage. Over subsequent decades, miniaturization and mass production reduced costs. By the 1970s and 80s, microwave ovens became common household appliances. A parallel technology emerged from agricultural research. Lyle Goodhue and William Sullivan, working under a United States Department of Agriculture contract in 1941, developed the aerosol spray can. The invention addressed insecticide delivery requirements for Pacific theater operations. Malaria and other insect-borne diseases caused more casualties than enemy action in some tropical campaigns. The aerosol can use a pressurized propellant to atomize and disperse liquid insecticide. Engineering challenges included valve design, can burst strength, and propellant selection. USDA safety notes specified pressure ratings and testing protocols. The device proved effective for mosquito control in tents, barracks, and field hospitals. After the war, aerosol technology transferred rapidly to civilian products. Paints, deodorants, hairsprays, and numerous other products adopted the pressurized spray can format. Valve standards and propellant regulations evolved, but the basic mechanism remained unchanged. The wartime innovation became ubiquitous in consumer packaging. The cause and effect chain connected tactical requirements to domestic applications. Detection advantages in maritime and night operations drove magnetron development. A laboratory observation during peacetime research revealed an unexpected application. Agricultural pest control needs produced a delivery mechanism that transformed consumer product packaging. By the early 21st century, microwave ovens numbered in the hundreds of millions of households worldwide. Aerosol cans appeared in billions of units annually across dozens of product categories. Both technologies originated from wartime development programs addressing specific military requirements. Both transitioned to civilian use with fundamental mechanisms intact. A radar lab incident evolved into an appliance counted in hundreds of millions of homes. An insecticide delivery system became standard packaging for consumer products. The applications were unforeseen in 1943, but the technologies were real, documented, and measurable. Algiers, New Delhi, Brisbane, 1st June 1944. A logistics operations center consolidated returns from 3 theaters. The dashboard displayed container performance, adhesive tape metrics, tire availability, and antibiotic distribution. Staff officers had anticipated marginal improvements from standardization and new procurement. The compiled data showed step changes rather than incremental gains. Fuel loss rates provided the clearest example. British and American forces had measured wastage at 15 to 20% when using traditional 2-gallon and 4-gallon tins. Leakage during transport, spillage during transfer, and losses from corrosion accounted for most waste. After conversion to 20-liter jerrycans, loss rates fell below 1% in most supply chains. A North Africa supply report documented the change. Fuel wastage on issue materially reduced post-conversion. The arithmetic was straightforward. A single month's saved fuel in one theater equaled the cargo capacity of a small coastal tanker. That fuel was available for mobile operations without requiring an additional supply convoy, escort vessels, or port handling. The operational reach gained from better containerization was measurable in kilometers of advance and hours of vehicle operation. Crate opening times showed similar improvements. Switching from paper tape to cloth-backed waterproof tape reduced opening time by approximately 30 seconds per crate. Across a battalion handling hundreds of crates daily, the cumulative time savings reached tens of man-hours per day. Those hours were available for other tasks, and the faster access to supplies during combat or time-sensitive operations had tactical value that exceeded simple labor accounting. Infection mortality reductions were documented in surgical theater reports. Hospitals that implemented penicillin protocols for wound care showed double-digit percentage point reductions in infection-related deaths. Controlled trials and field data converged on similar results. Faster, more effective treatment reduced hospital stays and medical evacuations. Beds turned over more quickly. Fewer soldiers required long-term care or medical repatriation. Tire and rubber product availability stabilized as GRS production reached steady state. Vehicle immobilization rates from tire failures dropped. Maintenance officers could plan replacement schedules based on mileage and load rather than scarcity. Convoy planners counted on predictable vehicle availability rather than estimating attrition from rubber shortages. The operational tempo improved because logistics became more predictable. Theater quartermasters compiled the effects: higher march rates, more sorties flown, faster cargo handling at depots, reduced casualties from delayed medical treatment. The individual improvements were measured in seconds, liters, and percentage points. The cumulative effect was operational reach and survivability. A Mediterranean theater staff analysis calculated that jerrycan adoption alone had increased effective fuel availability by 15%. Without adding a single additional tanker or supply truck. The increase came entirely from reduced waste. Duct tape reduced ammunition resupply time during sustained operations. Penicillin returned soldiers to duty weeks earlier than previous infection treatment protocols. The numbers challenged pre-war assumptions about what constituted strategic advantage. Commanders had focused on weapons, tactics, and troop quality. Logistics staff demonstrated that container design, packaging tape, and antibiotic production were equally decisive. Minutes and liters accumulated into operational tempo. Reduced infection mortality, maintained force strength. The dashboard provided a composite picture. No single innovation was independently decisive. The cumulative effect of standardized containers, improved adhesives, synthetic rubber, antibiotics, instant coffee, and microwave technology created advantages that multiplied across logistics chains. Each improvement reduced friction. Each reduction in friction increased operational capacity. By mid-1944, Allied forces operated with supply chains that were faster, more reliable, and less wasteful than any previous military logistics system. The improvements were not metaphorical. They were quantified, documented, and measurable. The data showed that industrial standardization and specification-driven procurement had changed the arithmetic of operational planning. A single month's saved fuel equaled a small tanker's cargo. That was reach gained without one extra vehicle, one extra convoy, or one extra crew. The advantage came from containerization. Detroit, London, 15th July, 1944. Draft pages for Mill and British standards documents showed thread pitches, adhesive peel minimums, and accelerated corrosion test cycles. Engineers from the United States National Bureau of Standards and editors from the British Ministry of Supply reviewed the specifications. The documents formalized what had begun as field expedients and theater-level solutions. Theatre staff had expected improvisations to remain local. Instead, procurement offices moved quickly to standardize successful designs across all services and allied nations. The logic was operational: interchangeability reduced inventory complexity, simplified maintenance, and allowed cross-theatre supply transfers without compatibility concerns. Unified can volumes and cap dimensions appeared first: 20-liter fuel cans, 5-gallon water cans, and smaller containers for lubricants received dimensional tolerances that ensured stacking stability and spout compatibility. Gasket compounds faced standardized squeeze and temperature resistance tests. Interior coatings required minimum adhesion and corrosion resistance verified by salt spray chambers and petroleum immersion. Adhesive specifications defined peel strength minimums by test method. Cotton duct tape underwent 24-hour water immersion, followed by peel testing at controlled rates. Minimum values were set at levels that field trials had shown to be effective. Acceptance sampling tables determined how many units per production lot required testing before a batch could ship. Ration packaging specifications covered burst strength, tear resistance, and moisture vapor transmission rates. Laminated cartons, waxed barriers, and heat-sealed envelopes all received quantitative performance requirements. Quick open seam designs followed prescribed geometries to ensure consistent opening times. Sterilization protocols for medical packaging appeared in separate annexes. Disposable tubing, plasma containers, and antibiotic vials required sterilization validation before use. Pressure ratings for aerosol cans specified burst strength with safety margins. The specifications were technical, detailed, and binding. A standardization directive made the policy explicit: interchangeability is mandatory where practicable. The phrase "where practicable" acknowledged engineering constraints, but the directive's intent was clear. Components from different manufacturers would meet identical dimensional and performance standards. The cause and effect relationship extended beyond immediate military needs. Post-war manufacturers retained the wartime gauges, test methods, and performance criteria. Converting military production lines to civilian output required minimal capital investment. When the specifications remained valid, consumer products inherited military testing protocols because those protocols had been proven in the field. The transition was documented in procurement files and conversion memos. Companies that had supplied jerry cans to the military began selling identical cans to gas stations and civil defense agencies. Adhesive tape manufacturers shifted from military to hardware store distribution with unchanged formulations. The three-handle fuel can geometry and cotton duct tape specifications persisted with minimal revision. Building codes, automotive standards, and consumer safety regulations incorporated test methods developed during the war. Pressure vessel ratings, adhesive peel strengths, and corrosion resistance requirements that had been written for military procurement became civilian engineering standards. The specifications had been validated under the most demanding conditions imaginable. Peacetime applications were, by comparison, less severe. By the late 1940s, multiple industries operated under de facto mil-spec standards, even for civilian products. The specifications had become defaults because they worked, they were proven, and the tooling already existed. Wartime standardization turned into permanent industrial practice. Newark, New Jersey, Manchester, UK, 10th November 1944 to 31st December 1945. A procurement officer in Newark signed drawdown orders as European combat operations wound down. Across the Atlantic, a Manchester plant manager changed signage from military contract fulfillment to civilian packaging. The transition had been anticipated since mid-1944, when Allied victory became statistically probable rather than merely hoped for. War-only production lines were expected to shut down after demobilization. Instead, many converted directly to consumer supply with minimal retooling. The reason was straightforward: wartime specifications had solved real problems that peacetime consumers also faced. Moisture resistance, durability, quick opening, and sanitation were equally valuable in hardware stores, kitchens, and clinics as they had been in combat zones. Raytheon's commercialization teams filed microwave oven patents, focusing on restaurant and industrial applications. The magnetron technology that had enabled airborne radar could heat food rapidly and uniformly. Early commercial units were large and expensive, but the path to mass production was clear. Engineers developed safety interlocks, door seals, and control systems that met emerging electrical safety codes. Johnson & Johnson product managers reviewed duct tape specifications for retail distribution. The cloth-backed, waterproof, rubber-adhesive tape required no changes. The same formulation and manufacturing process that had sealed ammunition crates worked for home repairs, automotive maintenance, and construction applications. The company launched consumer SKUs with packaging that emphasized the tape's versatility and water resistance. Nestlé marketing teams prepared instant coffee for supermarket distribution. Spray-dried and freeze-dried coffee powders that had been developed for combat rations transitioned to retail with brand names and consumer-oriented packaging. The moisture barrier envelopes became foil-lined jars and tins. The product itself remained chemically identical to the military version, jerrycan. Manufacturers pursued licensing agreements for civil fuel and water handling. Gas stations, municipal water departments, and civil defense agencies required portable containers with the same durability and handling characteristics that had made the jerrycan successful in military logistics. The 20-liter capacity, three-handle design, and cam-lock closure became standard features in civilian fuel cans. Military helicopter development, particularly the Sikorsky R-4 used for medical evacuation trials, informed post-war emergency medical services aviation. The concept of rapid aerial transport for critically injured patients from accident scenes to hospitals derived directly from battlefield medevac protocols. Civilian air ambulance services adopted similar procedures and equipment. Retail packaging inherited wartime moisture barriers and quick-open seam designs. Cardboard cartons with waxed coatings, heat-sealed edges, and tear strips became common in grocery stores. The engineering that had kept rations dry in tropical humidity worked equally well for breakfast cereals and snack foods. Aerosol valve standards migrated from insecticide delivery to paints, lubricants, and personal care products. The pressurized spray mechanism proved useful for dozens of consumer applications. Propellant regulations evolved, but the basic can design and valve mechanism remained largely unchanged from wartime specifications. A conversion memo captured the economic logic: existing plants suitable for continued civilian production without major capital outlay. Factories that had tooled up for military contracts could serve consumer markets by changing labels and distribution channels rather than rebuilding production lines. The continuity of supply normalized wartime products in peacetime life. Hardware stores stocked duct tape. Supermarkets carried instant coffee, gas stations used jerrycans for emergency fuel, hospitals adopted single-use sterile packaging for medical supplies, aerosol cans appeared in garages and bathrooms. By 1946, products born of emergency procurement were present in homes, garages, clinics, and municipal infrastructure. The transition from military to civilian use was not metaphorical. It was direct, documented, and economically rational. The specifications had been proven under demanding conditions. Peacetime applications simply required wider distribution. Geneva, Washington, 1946 to 1960. Statistical yearbooks compiled by trade organizations and government agencies documented post-war production volumes. Synthetic rubber, antibiotics, consumer packaging, and household appliances appeared in annual tables. The numbers revealed a pattern. Wartime production levels had not collapsed after demobilization. Instead, they had become baselines for peacetime industry. Global synthetic rubber output reached millions of tons annually by the early 1950s. The figure exceeded total pre-war natural rubber consumption in many product categories. Tire manufacturers, industrial equipment makers, and consumer goods companies had shifted permanently to synthetic elastomers for applications where the material properties were adequate or superior to natural rubber. Natural latex retained advantages in certain specialized uses, but the majority of rubber products now came from polymerization plants. Antibiotic production expanded beyond penicillin to include streptomycin, tetracycline, and other compounds. The fermentation technology, quality control protocols, and distribution networks established during the war provided the infrastructure for rapid pharmaceutical development. Annual production volumes measured in the billions of doses. Infection fatality rates in peacetime hospitals fell to fractions of pre-war levels. The statistical correlation between antibiotic availability and surgical outcomes was unambiguous. Aerosol valve and can standards proliferated across consumer product categories. Paints, lubricants, hairsprays, deodorants, and insecticides adopted pressurized spray delivery. The valve mechanism and safety standards originated from wartime insecticide cans. By 1960, aerosol products numbered in the billions of units annually. Microwave ovens entered mass production more gradually. Early commercial units from the late 1940s served restaurants and industrial kitchens. Miniaturization and cost reduction accelerated in the 1960s and 70s. By 1980, microwave ovens had become common household appliances in developed nations. The cavity magnetron that had enabled wartime radar now heated food in millions of kitchens. Duct tape became ubiquitous in hardware stores, construction sites, and maintenance facilities. The cloth-backed, waterproof adhesive tape retained its wartime formulation. Manufacturers produced millions of rolls annually for consumer, industrial, and municipal use. The product required no significant redesign because the original specification had solved the fundamental problems of adhesion, water resistance, and durability. Jerrycan geometry persisted in civil defense, automotive, and infrastructure applications. Fuel and water containers for civilian use followed the same pressed steel construction, three-handle configuration, and cam lock closure that had reduced military fuel losses to near zero. International standards eventually codified dimensions and features derived from the wartime jerrycan. Trade reports documented the continuity. A statistical analysis from the late 1950s noted post-war consumption of synthetic elastomers now exceeds pre-war natural rubber imports across multiple industrial sectors. Health statistics tracked infection fatality reductions in peacetime surgical procedures, showing improvements consistent with antibiotic availability. The cause and effect relationship was measurable. Wartime design logic, moisture resistance, opening, speed, modularity, sanitation, standardization had become civilian reliability norms. Engineers and procurement officers applied the same principles to consumer products that had proven effective in military logistics. Test methods, dimensional tolerances, and performance requirements carried over from mil-spec documents to civilian standards. The products marketed as innovations in the 1950s and 60s were often wartime specifications under new brand names. Instant coffee, duct tape, aerosol sprays, synthetic rubber tires, and sterile medical packaging had all been developed or scaled during the war. Peacetime consumers purchased products that existed because of military procurement priorities from a decade earlier. The statistical evidence showed that the industrial mobilization of 1942 through 1945 had created permanent capacity and permanent standards. The factories, test methods, and specifications built for emergency use became the foundation for post-war consumer markets. The transition was not accidental. It was economically efficient and technically proven. Many innovations marketed in the 1950s and 1960s were wartime specifications under new brands. National Archives, 1965. A researcher at the National Archives cross-indexed War Production Board files, Office of Scientific Research and Development contracts, and Quartermaster Corps procurement records with post-war commercial catalogs and patent filings. The exercise revealed direct lineages from wartime specifications to civilian products. Popular military histories emphasized battles, campaigns, and commanders. The procurement files told a different story. Test sheets and specifications had shaped daily life as much as tactical victories. The documented connections were precise and traceable. Vesta Stout's May 1943 letter describing ammunition box failures mapped directly to Johnson & Johnson's Penicillin duct tape specifications and subsequent retail SKUs. The cloth backing, rubber adhesive, and waterproofing requirements appeared unchanged in consumer product formulations. The tape sold in hardware stores in 1965 was chemically and structurally identical to the tape supplied to ordnance depots in 1944. Cavity magnetron trial notes from the Telecommunications Research Establishment and Raytheon Corporation's post-war research logs connected directly to microwave oven patents. Percy Spencer's observation of chocolate melting near an active magnetron led to systematic food heating experiments. The patents filed in the late 1940s specified shielding, interlocks, and waveguide designs that would define microwave oven safety standards for decades. GRS production tables from the Rubber Reserve Program traced forward to post-war tire manufacturing and gasket markets. The emulsion polymerization process, Mooney viscosity controls, and compounding formulas developed during the war remained industry standards. Tire manufacturers continued using synthetic rubber for passenger and commercial vehicles because the material properties were adequate and supply was reliable. Quartermaster Corps' soluble coffee specifications connected to supermarket instant coffee brands. The spray drying and freeze drying processes, moisture barrier packaging, and reconstitution times established during the war carried over to civilian production. Nestlé and other companies scaled their wartime production lines for consumer markets with minimal modification. Jerrycan technical drawings from Allied copying of captured Wehrmacht containers mapped to automotive fuel container standards and civil defense specifications. The 20-liter capacity, three-handle design, cam lock closure, and internal lining became standardized features across national and international fuel handling codes. An archival summary note credited wartime standardization with achieving cross-service integration interchangeability that civilian industries later retained. Dimensional and performance baselines established for military procurement were subsequently adopted in consumer product standards and building codes. The language was bureaucratic, but the implication was significant. Modern product specifications descended directly from wartime procurement doctrine. The researcher compiled examples. Mil-spec thread pitches appeared in commercial fastener catalogs. Adhesive peel strength test methods from wartime packaging specifications appeared in ASTM standards for consumer tapes. Pressure ratings for aerosol cans followed safety factors developed for wartime insecticide delivery. Sterilization protocols for medical packaging established during penicillin distribution informed FDA requirements for disposable medical devices. The cause and effect chain was documented in contract files, test reports, and patent applications. Procurement officers had not intended to design consumer products. They had intended to solve immediate military logistics problems. The solutions proved so effective that they became permanent standards. The procurement doctrine emphasized measurable performance, interchangeability, and reliability. Those priorities translated directly into consumer expectations. Post-war buyers expected products that opened quickly, resisted moisture, functioned reliably, and used standardized parts. Those expectations originated from wartime specifications. By the mid-1960s, multiple consumer goods conformed to dimensions and performance metrics established 2 decades earlier during military procurement. The continuity was measurable. A survey found fuel cans, adhesive tapes, instant coffee formulations, and sterile medical packaging that matched wartime specifications within measurement tolerances. The archival record documented that emergency engineering had become everyday life. The products were not metaphorically similar. They were technically identical, or nearly so. The specifications written under wartime urgency had proven so effective that they required no significant revision for civilian applications. The war ended. The specifications did not. Between 1942 and 1945, Allied procurement agencies converted frontline operational constraints into codified product specifications. Moisture, contamination, corrosion, handling speed, and microbial infection risk became engineering problems with quantified solutions. The results were measurable. Fuel loss collapsed from double-digit percentages to near zero with jerrycans. Crate opening times shortened by tens of seconds with cloth-back tape. Wound infection mortality fell by double-digit percentage points as penicillin production scaled. Vehicle availability stabilized when synthetic rubber eliminated tire shortages. Preparation time decreased with instant coffee and redesigned rations. Detection ranges improved with compact radar, laying technical groundwork for microwave ovens. Each improvement reduced friction in logistics chains. Each reduction in friction increased operational capacity. The cumulative advantage was decisive. The specifications outlasted the emergency. Factories retained gauges and test methods. Consumer products inherited military performance standards. Building codes and safety regulations adopted wartime-proven protocols. The containerization, packaging, pharmaceutical production, and standardization infrastructure built between 1942 and 1945 became the foundation for post-war industrial capacity. By the mid-1960s, households, garages, clinics, and infrastructure systems used products conforming to specifications written during total war. The continuity was not accidental. It was efficient, proven, and permanent. The war ended. The specifications did not.